Okay, so I'm not quite sure why they gave me the big room for this, but I just kind of wanted to go over a little bit of how we kind of hit a challenge of we had issues with getting data from our fun little RAID, and this is kind of like a case study of kind of how we solved it, challenges we ran into along the way, and this may apply to you because there's a lot of systems out there using really high transactional systems that need some kind of hybrid SAN or some kind of background system that can handle lots of transactions. So nothing crazy. You probably don't know me. I'm not one of the core developers. I'm not a main guy. So I just work at a Peak 6 OptionsHouse. They're a company actually here in Chicago. They do a lot of high-frequency trading. And what I'd like to get into first, I'm about to show you a graph that I hope is self-explanatory. So you'll probably notice a little bit right before 8:30 and right about to 3, you've got nothing. It's just complete dead space. Well, the reason that's dead is because there's a lot of things that control how the market works. You can only trade during certain hours. You can only submit transactions during certain hours. There's APIs we have to call on. Basically, it's very similar to what you see on a trading stockroom floor. There will be nothing, and then all of a sudden the bell will ring, and then everybody starts yelling. Well, that's pretty much what happens here. We have an online system, and there's nothing, 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 and 8:30 the bell rings, and suddenly everyone starts logging in and going crazy. So you'll notice that right there, from about 8:30 to 9-ish, it's a little jagged. It's not a straight up. Well, there's a reason for that. If you look at that top line, that almost says 12,000 transactions per second. I'm getting this information, by the way, from the PG database stat view, if you want to check that out for yourselves. It actually has some stats on number of transactions committed and number of transactions rolled back. So you can get that information. It's really handy. But it just so happens that through this particular realm of time, we're handling roughly 250 million transactions. I'm not inflating that in any way. That actually comes from all of our front-end applications. We have about a half a dozen application servers that are all hitting this simultaneously. And the thing about traders is they always have 3 or 4 screens open. And each screen has like 5 iframes of information about how the stocks are changing and how their positions look. And it really is, each single person logged in can have like 3 or 4 transactions running simultaneously on our database, even with all the caching. And the thing is, we cache a lot of this data. We cache the stock positions, we cache their log information, their preferences. We pretty much try to limit the amount of activity to the database. But a lot of this is write heavy. So what you see here is actually the true transactional output. And the problem with that is sometimes your storage can't really handle that kind of level of activity. If you don't have a giant hybrid SAN that has like 30, 50 spindles in it, you're going to run into a problem. We ran into a problem. This is our database disk I/O graph. The number is actually obtained from IOstat, which is a handy utility. My favorite command line options for that are -dmx to give me an extended view of what's going on. And that particular last column we see here is the disk utilization. Basically, how saturated is its activity? Can it write or read any more than it's possibly doing right now? The answer in our case, starting around 8:30, is no. You probably see this a little bit before that. That's all batch processing and some earlier jobs that run. And we can handle that. That's fine. We don't like the fact that it got up to 100% for almost an hour, but it's handleable. But as soon as 8:30 runs, 8:30 hits, we can't really have 100% disk I/O and try to serve 12,000 transactions a second, because we're going to have to start getting timeouts in the application side. And customers tend to notice that. The problem that's actually here that we don't really explain, though, is what happens if there's an I/O spike you don't anticipate? Or what happens if, God forbid, your database crashes? Suddenly all your caches on your OS level are gone. Or they're invalidated in some way. Or there's other problems you're going to run into. And then suddenly that 100% right there from 8:30 to 9 is a lot worse, because none of it's cached now. So we were able to serve the 12,000 transactions a second because a lot of that was cached. That cannot come from the RAID we had. In an event of a crash, it's actually going to be at 100% for 2 hours. And suddenly we can only serve maybe 2,000 transactions a second. And suddenly we have to scale all of our systems back. We have to scale all of our refreshes back. And customers are like, well, why isn't my data refreshing anymore? And they'll go elsewhere. This is a problem you can run into with a highly transactional system because a lot of it's based on I/O. You got to get the data from somewhere, and it can't always be cached. And if your data is really big, sometimes just simply going in and out of memory will be enough disk I/O. Like you'll notice after, even after it settles down, it's still around 20%. And that's just churn, stuff going in and out of cache because we had a 300 gig database and only 30 gigs of RAM. You fix that by adding more RAM, but that still only reduces a certain amount because you can't cache the whole database unless you have a lot of RAM. So what we actually had was a roughly 1,100 transactions capable system. This is measured using PGBench, and it's not completely analogous, but it's close enough for government work. So when I mentioned that if the database ever went down, suddenly when we go from 12,000 transactions a second to that, suddenly it becomes a problem. So that was the peak measurement you probably saw on the graph. And here's an element that could be problematic that a lot of new databases encounter: customer acquisition. Our particular case, we grow by about 100% a year. So it's basically a factor of 2 exponential. So the way that works is we accumulate as much data this year as we had all the previous years combined. We also accumulate as many customers this year as all the previous years combined. The problem with that is that 11,500 transactions per second will need to increase by 100% when all the other years behind. And we have that TPS in the backing store, which is, it was great. It was, it was a terabyte and a half of space, but it couldn't serve. So, what are things that can break your cache? You wouldn't expect that, but it can. It reads your entire database from beginning to end. And if you have a 300, 400, 500 gig database, terabyte database, unless you have a terabyte of RAM, you're going to kick stuff that you want in memory out of memory. Maintenance. Back up your database. Same problem. Heaven forbid you get a Cartesian product or something crazy or a report that runs that you weren't expecting. We have a reporting database. Sometimes the developer takes it on himself to accidentally run on the wrong server. It happens. And on a transactional system, we try to limit that as much as possible. You can't always stop it. Or you have a giant table that's used for reconciliation that's required for, say, SEC compliance, and it needs to be on the production server, and someone misses a where clause. That table is half the database. So it's going to kick out all those handy tables you actually care about, like orders, preferences, login IDs, authentication tokens, gone, because someone accidentally read the 150 gig table. And database dumps, which I hope you're doing. So what can we do to fix this? How do we reboot our caches? Well, there's a lot of different ways to do this. So PG class has a handy couple of fields in there. Rel file node is one of them that tells you where on disk your actual tables live. So if you know which tables are really active, you can identify them and make a quick script that says, okay, DD, just read these into memory for me. And then they'll be OS cached, and that at least is a start. Even for big databases, as long as you have disk bandwidth, That'll take like 5, 6 minutes because they're all straight sequence scans. Or, as Greg Smith likes to tout quite often, PG Fin Core, which is a far more elegant system because it actually takes into consideration what was in memory at the time you snapshotted it, and it can put it back into place. There is a slight limitation with this because you have turnover and churn, which you can't really stop. And like I said earlier, if you have a giant database and small memory, or even big memory, you can't always cache everything. And you'll still get some churn that may be more than the transactions per second you want to handle can handle. So MacGyver would be proud. There's always some kind of hackneyed, structure we're building that can do this kind of thing. And there's really no built-in way, unfortunately, to kind of come back from a catastrophic failure. And it doesn't solve database turnover. So I'd like to, I guess, relay a short story that kind of may illustrate this a little bit. So while we were doing this search for, trying to figure out what was wrong with our I/O, we actually found a semi-solution. We added a bunch of RAM, and we actually run Enterprise DB's product. Well, for a while, we were using infinite cache, which is kind of basically a memcached layer that replaces your shared buffers. After it gets kicked out of memory, it goes into your infinite cache instead, which is great. It totally sped up our system, added a lot more RAM because we were able to have like 2 or 3 servers and share the RAM with the database. But there was a small bug in the system that was patched later, and we added the patch. But while that bug was there was a subtle edge case that would cause index corruption. And they patched this a couple of months ago, but earlier versions of Postgres Enterprise DB, if they encountered index corruption while doing an index read, it would panic and shut down. It did this to us in the middle of the day around 10 o'clock where you see that graph hit its peak. We brought it back up. That was probably our first mistake. We brought it back up because we wanted it up now. The database can never go down. Since it's a financial sector, if it goes down for more than a mere period of time, people can literally lose millions. We have $1 billion of customer finances in our system right now. And it went down. So it comes back up, and 1,000 transactions a second. Oops. For an hour. We scaled back all the systems. The database was up, but it was definitely limping. Somebody shot it in the leg, and it was kind of going along. So these are the problems you encounter when you're running a high transactional system. You need to have a really, really fast back end. So how do we fix this? Well, there's a lot of different ways. Get a big-ass SAN. EMC makes a good one. RamSAN makes a really good one. Their first, maybe not their first foray into the structure. They had basically RDRAM backed by SSDs. That's pretty good. You can't really get any faster than that. And Whiptail makes a nice, I would not quite call it consumer grade, but they basically took a lot of OCZ SSDs and stuffed them into a 2U cabinet that they kind of sell for about 200 grand. But that's their solution for really, it has really high transactional output. It's pretty fast, and it's got built-in data compression and all the fancy things you'd expect from a SAN. But let's move on. SSDs. Just get a big old external cabinet filled full of SSDs. Intel makes some good ones, OCZ, Corsair, lots of good ones out there. Or get some PCIe cards. These are relatively new. There's, RamSAN again makes a couple of these. Fusion.io and Virident, good products. Some of them use single-layer NVRam cells instead of multi-layer. Just lots of different technology out there you can choose from. So let's break this down a little bit more. So SANs are awesome, but they're expensive. I mean, you have a 4U at minimum cabinet, and you probably have the larger one where it's actually the whole cabinet. full of disks. That's not cheap. The disks aren't cheap. The management software is not cheap. Nothing about it is cheap. You pay for that. And the other thing, a lot of older SANs are still based on regular spinning Rust, and that means you have to have a cabinet full of like 50, 60 drives to get the transactional output you actually need to serve your transactions per second directly off disk, because, like I said, it can't always be cached right away. And they're pretty darn big, because disks are pretty darn big, even with their SSDs. So what about SSDs instead? Well, they're still kind of expensive. Not great, but the other problem is SSDs, and they don't really, it's not quite an advertised fact, but some of the other SSDs that are available and NVRam SANs sometimes combine the actual NVRam chips in the back end using some kind of RAID technology. You might not want that. Maybe you just want to access the cells directly. Maybe the RAID element causes write amplification, which is a problem with NVRam because NVRam does not like to write. So all right, so these are kind of the elements with new SSDs. Corsair makes a couple of good ones that I've mentioned that do this. So does Intel and LCZ also. Samsung too. They're, what, 2 orders of magnitude faster than disks as far as random I/O. And with something like if you get the right drivers, or if you use ZFS, you can use them as a intent log or a pass-through cache. And that can drastically speed up even using them as a backing store on a larger disk array. And because databases, and because NVRam hates to write things, usually have built-in deduplication because they don't want to write to the RAM as much as possible. This is a problem that Greg kind of brought up in the mailing list earlier. And this is a problem that faces all of us. If you want high transactions, you need also integrity. And a lot of the earlier SSDs, and even some of these later ones that are consumer level or even some of the professional level, do not have capacitor-backed cache. And why is this important? Well, if you know anything about NVRam, or if you even tried to experiment with it, NVRam is actually kind of slow writing sometimes. And a lot of these drives will use DRAM or RDRAM or some kind of backing that will kind of cache that write while it's happening to try to get to the disk as fast as possible. But if you talk to the disk controller, it will actually say it wrote it. So if, heaven forbid, you lose power while it's doing that, you lose data. Your database thinks everything's fine. The OS thinks everything's fine. The drive says everything's fine, but it lied to you. The capacitors need to be there to actually let the drive finish writing, even when a power loss occurs. And only newer drives have that, and not all of them do. The other problem is a lot of the drives that are out there rely on trim support. And trim support basically tells the controller to say, well, here, clean up all this old data, because as a NVRam cell gets more full, it gets slower. It needs to have kind of an excess scratch area to kind of move data around, otherwise it starts getting slower and slower for writes. And with trim support, you're not going to find a lot of RAID cards that support trim. Some OSs don't even support it. Later versions of Linux do, Windows does now, and it's all available, but at the time this happened to us, 2010, this was very rare. Getting a RAID controller that actually had trim support, and even finding a cabinet that lets you put SSDs in it that's not, HP didn't sell one, Dell didn't sell one. We couldn't actually get one commercially unless we went to one of the smaller vendors, and we only use Dells and HP right now. So that can be a difficulty. If you don't have trim, your RAID will slowly get slower and slower and slower until finally it may be only a little bit faster than disk. And you won't even know it until you start actually running disk scans and analysis. And some, in the case of Corsair and a couple of others, may have overly aggressive garbage collection. So some of these drives, in order to get around the trim problem, have implemented their own firmware level garbage collection. And as early efforts in this case are, sometimes they're a little over aggressive. And this can actually drastically shorten the life of your SSD, which is exactly what you don't want if you're running a giant, RAID full of these things. So what's our other solution? PCI cards. So they're basically the same thing as SSDs with a few minor changes. So they can talk directly over the PCIe bus, which doesn't have the limitations of SATA, SATA 2, SATA 3.0, SATA 6. It's basically just straight over PCI bus. You can transmit as fast as the background bus can go, theoretically. And there could be pass-through drivers. Since these cards directly integrate into the system, they're basically a component of the actual hardware. So in a lot of cases, the vendors of these cards supply drivers, and while that makes these cards not bootable, it means you can get a lot more control over what they do. And in this case, you can say, add an interface layer in Windows or Linux or whatever, and call them a pass-through. So writes go to this, and then, writes get passed through the card to the disk. Reads go through this, and it becomes a second-level persistent cache. So in this case, if our database had gone down at the time it did, it would have come right back up. And kind of like I mentioned, they're basically available raw. SSDs come as SSDs. You can use them as a device on the IDE channel or a SCSI channel, whatever. The raw configuration here, what I mean is you can talk directly to the cell because it's basically just a mounted device at that point. In the case of Fusion IO, at least, I'm not sure about Viridin or Ramsan, if a card has two cells on it, you can mount them separately as separate LUNs, or you can combine them with a RAID 10 or some other kind of method to actually get more space or more reliability or more speed. And you don't have to worry about the card doing that because you can just use an LVM or LVM2 or some kind of add-on level. So it's all software level. But because SSD is so much faster, you don't have to worry about rebuilds being slow or that being a problem as you might with a regular drive. And every case that I've seen, I'm not sure about OCZ, but Viridin, Ramsan, and Fusion IO all have capacitor back caches. They're not going to lose your data unless the cell fries itself. And that's probably a lot more rare than power loss. There's a bit of problem, though. They're still pretty expensive. In the case of Fusion IO, Ramsan, and Viridin, you're probably looking at least $5,000 for their lowest end product. And if you have a dual node failover system where you normally mount one external device, you can't really do that with PCI cards, right? Because they're plugged into the computer. So you've got to use DRBD or some kind of replication system to basically make sure that the data on one node is on the other in case of a node failure. If you're trying to be like highly transaction and crash recovery safe. And if you're a financial institution or something where uptime is pretty much critical, you have to buy two of these things. So that's pretty steep. So let's get to the actual numbers that you may have actually probably been waiting for, not just the crazy graphs in the beginning. So I ran a few tests when we got a few of these sample cards. Initially, we were when we first got this idea, we're like, oh, we can get these PCI cards because SSDs aren't quite right. We don't really want to spend $500,000 on a SAN. Actually, 3 SANs because we've got production, stage, and disaster recovery, and they all have to be exactly the same if we want to do proper rollouts. So eventually, we're like, oh, we just saw this ad for an OCZ card that does like 100,000 IOPS or some ridiculous number. But unfortunately, OCZ was also having a lot of complaints if you actually followed the different boards and whatever that followed these cards. And that's how we actually found Fusion IO. Probably heard of Steve Wozniak. He's actually on the board of directors for Fusion IO. So his notoriety kind of gave us the kind of clue to at least get a few sample cards from them because, hey, any company like this will give you sample cards. Hell, they practically throw them at you because they want you to buy them, right? So we got 2 of these, and we threw them in a test server. And I ran a few PG bench tests. I probably ran hundreds of these things over the course of a week. The basic structure of my test, though, was I put the scale of 1,000, so this was a pretty big database. started at 10 clients up to 60, so it was a pretty large amount of clients, and each one of those ran 1,000 transactions. I actually ran this up to 5,000, 10,000, and 20,000 just to see if the numbers were consistent, and they seem to be. So the numbers I'm about to show are the maximums obtained from our disk array and from Fusion IO. So when I say 8-disk RAID, and on my earlier slide said 6, well, that's because we were actually doing a little bit of organization. When we first noticed our problems with throughput, we tried to save ourselves by restructuring our RAID. Well, we only had one cabinet. There was a limit of what we could do. And we went from something like 1,200 to our final read number was actually using a very minimal amount of short stroking. We were able to get it to roughly 1,600 transactions a second. This is from just a regular, like using the whole RAID. So mixed performance is 1370, read is 1440, roughly. So that's a good 30–40% improvement over what we had. That was pretty impressive, but it's not 12,000. And it's not even 6,000, which would have been pretty helpful too. The I/O drive we got from Fusion IO, on the other hand, now remember I'm comparing this to an 8-disk RAID, not just one, SSD or one drive. 5,760 write read performance. So you can see there that the writes completely degrade the performance as what you might expect. Because what you would expect, what you'd want, is that 17,300, that's the read performance, would stay consistent on the writes. And the thing is, the reads are boosting that number, because you know that the PG bench test with the mixed reads and writes, because it does select and update, both. I'm not quite sure how to scale how that worked, but the number of writes is probably around 2,000 maybe. It's much, much, much lower than the read performance, but it's the read performance we actually wanted, right? It's still roughly the same speed, or at least twice as fast as a 8-disk RAID, which we had before, so we didn't actually lose anything. In order to get this same performance from one Fusion IO card, we would have needed probably a 30 drive or more RAID. We would have needed 30 spindles or more in a RAID configuration. And this is a RAID 10, so that's pretty impressive, but that's also really expensive. It's really large. And you could probably get the same thing, I guess, with a hybrid SAN that has, a bunch of disks, some SSDs, and maybe a giant, 2 or 3 gig cache, or maybe more than that. But in order to do that, like I said, we would have had to spend $500,000 3 times to get it. Whereas this, $10,000 card, Or to match the read performance, and this is the crazy thing that actually shocked even me while I was running these tests. So an 8-disk RAID is not the same as one drive, right? And normally SSDs are about 100, 200 times faster than one drive. Well, this is 100 times faster than 8 drives, which is a little bit ridiculous. Wait, yeah, it's 10 times faster than 8 drives. But I have to multiply it out, so I'd have to get 80 drives plus hot spares, and yes? Right, right. Mm-hmm. Yeah, the one we have is actually their lowest, not quite the lowest model. It's the Fusion IO. No, it is the lowest end model, but it's the 640 terabyte one, or 640 gig one, not terabyte. That'd be amazing, but no, it's a 640 gig one, and it's not the Duo, which is actually 2 chips. Like I said before, you can actually address the cells directly if you want. If we got the Duo, instead of combining them in a RAID 0 or getting the space, we probably would have combined them with a RAID 10, or sorry, RAID 1, and actually got the throughput if we actually needed that. But we didn't, so we just didn't bother. But that would have been an option. And Fusion IO itself actually makes cards with 4 cells on them. They call them their quads, and they come up, 5 terabytes? were pretty big. So 100 drive RAID, can you imagine the cabinet with 100 drives in it? It's basically the entire cabinet, or maybe even 2, depending on what kind of product you buy, to get this kind of read performance. And remember, what we were trying to reach was the ability to have crash recovery, because we could have probably compromised by getting just a few more drives, like getting 30 drives probably would have been enough to boost the multiplier, because the problem is the difference between 1,200 transactions a second and 12,000 transactions a second is, it's a giant multiplier. So if we even tripled our amount of drives in our RAID, that probably would have helped tremendously. But it still wouldn't have been enough to come back right away, which is what our customers expect after a crash. Now, I will bring this up that doesn't really covered by my slides. If we were running Postgres 9, or Enterprise DB 9, we would have had asynchronous replication in place, and that would have meant all the machines would have been cached. And if one master failed, we can switch over to another one, its cache would have still been valid. Its data would have still been there. It would have been a direct failover. So this is actually one place Postgres could have saved us money if we were actually on the latest version. And it's something that a lot of databases couldn't have done. So I guess it's another advocacy thing for Postgres on our side. So in conclusion, I'd like to say our old disk performance, and with the Fusion IO, I did the same test, same chart. That bunch of batch processes is still kind of there. But you'll notice that the previous line, that red line, was the median for that particular time period. It was at 40%, right? Now it's at 10, and the performance converges around 10% instead of 20. So even after it's all cached, it's still doing much less work. And this is including writes. And the other thing is, since we only got the one card in each machine, our walls are also going there. So are the PGR and the archives transaction logs. So that's 2 extra sets of writes that were not happening on the RAID, because I only tested the data side. I didn't test the wall side. So that previous graph was just the plain data mount, the data LUN we had. So it was cheating, and it was still way behind. I'd like to point out some resources. So PGFinCore, this is a link out here. I actually have these slides, and I'll put this up on the wiki. This is a PDF file you'll be able to download, and all these links are active. But PGFinCore, ZFS, I kind of mentioned earlier, will let you put a ZFS intent log, and then there's another cache layer you can put in that will basically treat an SSD or even a card like this as a write-through cache. Fusion IO, of course, Ramsan, Virident, they all make very good products that you can decide with your own tests what you want to try out. Now, this is something that kind of shocked me. I didn't realize it existed. Dell actually makes PCIe chassis you can mount to other machines. So you can get a chassis with like 8 PCI expansions in it with hot pluggable modules. You can fill these with Fusion IO cards or whatever you decide to pick, and suddenly you can mount that on several machines, and you don't have to worry about single point of having multiple cards trapped in servers and having to do various migrations. You just plug it in with a fiber channel array. And of course, a link to us because we wrote all this, so, or at least this demonstration. I guess, yeah, I think that's really it. I'll take questions if there are any. I guess I sped through this a lot faster than I expected, which I apologize for, but at least now you get your break. Yeah? Yes, we did. And actually, at least in Fusion IO's case, they have SNMP traps that you can actually monitor. And one of the traps that you can monitor is the health. And that particular health comes straight from the firmware. And since the firmware controls a lot of the interaction with the cell itself, like how many reserve cells are available, how much of the card is still functional, you can actually watch as more cells degrade and, more parts of the card degrade and get worse or slower, or, the card starts performing badly, that will go down. Ours has been at 100%, even with our 300 million transactions a day, for the last 3 months. So the expected lifetime of these cards is usually about 3 years, roughly, because then, NVRam cells can only be written to a certain amount of time before you can stop writing to them and you can only read from them. But so far, we haven't had a problem. And the other thing with these cards, and most vendors do this, our 640 gig card is actually 900 gigs. So there's a giant amount of reserve for reusing cells or reallocating cells or even a scratch space so you get your high performance. That's how they're able to outperform an 8 gig RAID an 8 disk RAID by so much. Well, we deployed it in March, and we've been hitting it, like I said, pretty hard with pretty much everything we have on a 300 million transaction a second. We're actually running 6 of them. Yeah. Well, right. Well, here's the thing. One of the things we do, because we're a financial institution, we have to have pretty much promised uptime because we can get our asses sued off if we don't. We actually have an infrastructure that a lot of you are probably familiar with. To get the transactions per second we need, to get the reliability we need, we have dual node failovers, right? We have a disaster recovery, which is also a dual node failover. And each of those machines has a Fusion IO card in it, which is replicated using DRBD, which is monitored by a pacemaker, which is, there's several different layers of redundancy on top of all this stuff. So we actually have had a card fail, but not in production. It was actually in our disaster recovery environment. Card failed, the machine's basically useless. So we have the second node up for a while we get a card replaced. And as long as you get their, at least in Fusion IO's case, you get their advanced support, they'll send you a new card in the mail right away. Sometimes you can have a couple extra on the side, like in a box, just to make sure you have extras, and I would actually recommend that for any hardware you have. But at least in this case, it didn't hurt us that much. And it was our disaster recovery, but even if it was production, we still had another node. We were alerted to the failure by trying to bring up the machine, and the SNMP stuff was all failing, and our pacemaker stuff said, I can't bring this drive up, I'm just going to shut the machine off. So we basically turned it off, and we just waited to get a new card, plugged it in, and it just worked just fine. We actually just finished our migration to get off all of our old MSAs, and it's probably the most successful thing we did. It literally saved our butts in a couple of cases, because we did some crash recovery testing where we actually did some power polls. And we literally went to the interface for the power device for that rack and shut off the server, like without even asking. We're just yank. And like he mentioned the shoot the other node in the head kind of stuff. We shot the other node in the head several times in our staging environment over the course of a good month of testing. And with a test running, there was basically, we keep all of our transactions for the previous day, and we archive it because we have to. So we basically took that and replay it, and that's how we do our testing. So during one of those tests, we shot the other node in the head, and within about 30 seconds, pacemaker had switched over to the failover node, and it went from a load of 0 to a load of 5, back to a load of about 2 within 2 or 3 minutes. And if on our old hardware and our old MSA and our old RAID, that would have taken about half an hour at least. So, I mean, our vacuums have gone from 2 hours to 20 minutes. We can rebuild every index in the entire database in about half an hour, with a couple of exceptions because the tables have like 200 million rows in them. So that's just processor time at that point. But yeah, it's been really successful for us. And the thing is, if you have a highly transactional system, there's not many solutions out there without, without MacGyvering some kind of solution for yourself, or just buying a big old SAN and not caring about it. And if you don't, it's a challenge we faced, and this is how we solved it. I mean, there's a lot of different ways to do it, but these are the options that are available, at least right now. Like a couple years from now, who knows? And SSDs are definitely getting better, and I think I mentioned that a little bit, that they finally added the capacitor-backed caches. They finally gotten past the trim problem, and they just need to get a few tweaks, and there need to be a few more cabinets available that actually allow SSDs, because sometimes vendors like to sell their own stuff, and it's not as advanced as what you might find actually from other vendors when you can pick them out. Like you can't really buy an Intel from HP or Dell. You have to buy their unbranded thing that who knows what's in there. Anybody else? Yeah, we archive all of our walls on a third-party offsite resource. We archive them every day. They go to tape every week. We have archives going all the way back to 2006. Yeah, we didn't lose anything. It was all fine. The only other change we made aside from this is we switched from ext3 to XFS. So maybe in the future we'll decide to try ZFS, depending on how stable Fuse is with our Linux hardware, but that's pretty much it. Anything else? No? All right.